Interference and sound waves. We've seen this picture before. The interference of waves was covered earlier in this unit where 3 different types were covered, right down here. This concept is now applied to sound waves, but only constructive and destructive interference will be discussed. 2 sound sources, over here, red and green, emit sound with the same amplitude and wavelength and are switched on at the same time. For this first example, both waves travel the same path length, which is the distance to a listener. So that would be from here to here, where our listener is. The waves add together in constructive interference. The sound waves are in phase, and their sum will be a maximum, and the listener hears the loudest possible sound. And in phase means they hit the peaks at the same time, and they hit the troughs at the same time. Now move the red source so its waves travel a path length that is 1/2 lambda different from the green source. They will add together in destructive interference. The sound waves are completely out of phase. That means the peak of one is matching with the trough of the other, and their sum will be 0. The listener will not hear anything. The sound wave will be like this. Now move the red source closer to the listener so the sound waves travel a path length difference that is an odd multiple of 1/2 lambda. In this case, it will be 3/2 lambda. They will add together in destructive interference. The sound waves are completely out of phase and their sum will be 0. The listener will not hear anything. Finally, move the red source so the sound waves travel a path length difference that is an integer multiple of lambda. We're going to show 2 lambda this time. Right here's 2 lambda. That's the difference between where the green box is and the red box. They will add together in constructive interference. Right, you can just see a little bit here. It's rising up there and it's exactly matching that one. The sound waves are completely in phase and the listener will hear a maximum sound. Sound waves interfere in the same way that other waves do in space, whether it's water waves, sound waves, string waves, anything. Constructive interference occurs when 2 crests or 2 troughs meet. When the listener is located where constructive interference is occurring, there will be a loud spot. And that's these red dots over here. Destructive interference occurs when a crest and a trough meet. When a listener is located where destructive interference is occurring, there will be little or no sound. And this time it's happening at the green dots. That's your destructive interference. A microphone is placed at several places and the sounds are fed into an oscilloscope. And that's what this picture is giving us. Okay? That's from an oscilloscope. That shows the sound amplitudes. Destructive interference occurs along the radial bands indicated. So that's these bands here where you just see a very light color and there's no alternating between dark and light. It's just light. Constructive interference occurs when the scope shows alternating dark and light bands. So here's a dark band, then a light band, then a dark band, then a light band. So that is our constructive interference. Here's a view of 2 speakers separated by a distance d and a distance L from a microphone that can move up and down on a post to record the loudness of the sound from the speakers. The microphone records a pattern of alternating loud spots and places with no sound. The sound from each speaker, except for point A on the center line, travels a different path length before reaching the microphone. Right at point A here, both of them travel this distance here. Same path length from both speakers. If the difference in path lengths is an integer multiple of the wavelength, it results in a loud sound, constructive interference. If it is an odd integer multiple of half a wavelength, it results in no sound, destructive interference. So what would be happening there? Well, let's look over here. Here we have a loud spot. This wave travels that distance. The wave from this speaker will travel this distance. So hopefully you can see how those are different distances. If the difference in those is 1 lambda, right? Let's say this one here travels an extra distance of 1 lambda, the wavelength of the sound, then you will have constructive interference, any loud spot. The derivation of the locations of the maxima, which is constructive interference, and minima, destructive interference, will be shown in the electromagnetic waves unit. Here's the maxima, here's the minima, and hopefully you can see here's our integral number of wavelengths, and this term here gets us the odd number, the odd multiples of 1/2 lambda. M is the order of the interference fringe, 0, plus or minus 1, plus or minus 2, etc. Right, because you have fringes going up in that direction, and also it's symmetric with that direction. X is the distance on the post from the center line, point A. Caution, these equations are only valid when the angle theta is less than 15 degrees, as their derivations relied on the small angle approximation. We'll talk more about that also in the electromagnetic waves unit. So our negative values of X show the location of the fringes below the center line. That's down here. Positive values are above the center line. The central maximum, m equals 0, is on the center line here. And once again, here's our maxima, here's our minima, and the orders of the fringes are gotten from m equals 0, plus or minus 1, plus or minus 2, etc. Example 1. Two speakers separated by a distance of 0.75 meters are placed 12 meters from a listener. The speakers generate a sound with a wavelength of 0.20 meter. What is the distance between the central maximum and the first place where the listener detects maximum sound? So maximum sound requires constructive interference. So here's our equation. D is the distance between the speakers. L is the distance between the speakers and where you're listening for it. Lambda is the wavelength of the sound. And since they want the first place where you hear maximum sound, that's m is equal to 1. Substitute in those values and you get 3.2 meters. Two speakers separated by a distance of 0.75 meters are placed at a distance 12 meters from a listener. The speakers generate a sound with a wavelength of 0.20 meters. What is the distance between the central maximum and the first place where the listener detects no sound? Your central maximum is where m is equal to 0 for your constructive interference. But we want the first place where you hear no sound, so we want a minimum, so we use our destructive interference equation, but what do we use for m? Well, in this case, we use m is equal to 0. That'll be the first place where there is no sound. Substitute in our givens, and hopefully you can see, here's our half wavelength number, and our final answer is 1.6 meters. Waves can also interfere in time, and when their frequencies are similar, a resultant wave is formed that is characterized by beats. Since the original waves have different frequencies, the resultant wave will have periodic times of constructive, destructive, and partially destructive interference. Remember when I said we weren't going to deal with that in sound? Well, we're going to deal with it now for the beat frequency. This results in a periodic repetition of an amplitude pattern for the resultant wave. So here's our two waves that are working with each other. Here's the resultant. Over here, we draw that straight line down and we find out we have a maximum in both waves, and the resultant wave has a maximum. We'll find places where you have minima. And here's where the partially constructive comes in, partially destructive. You have all these other waves that are not 0, nor are they maximum. So you get all three different types of interference. The variation in amplitude over time creates a wah-wah sound. It's hard to say that. Tuning forks with similar frequencies can be used to illustrate the sound. Best way to hear that is to please click on that video so you can hear the wah-wah sound. The wah-wah sound from the alternating maximum amplitudes and minimum amplitudes of the resultant waves is this blue envelope. That's your wah-wah sound. The beat frequency is the difference in frequency of the two waves, F1 minus F2. The blue and green waves, over here, with frequencies of 300 Hz and 275 Hz are plotted together on the top graph. The single green wave on the bottom graph shows the sum of these two waves. The beat frequency is 25 Hz, 300 Hz minus 275 Hz. Two speakers emit sound waves of different frequencies. The first is 525 Hz, the second is 528 Hz. What beat frequency is heard? We are given two waves with different frequencies that are very close to each other. So the beat frequency is the difference between those two emitted frequencies. So F2 minus F1, 528 Hz minus 525 Hz. The beat frequency is 3 Hz.